Hi, in this video, we're going to be working in chapter 9, which is about hypothesis testing. It's our first chapter on hypothesis testing. We'll have a couple more. And this is section 1. So we're going to be working on sort of like an overview of how it works. So of how the hypothesis testing procedure that we'll be studying works. I'm going to begin by sharing my screen, picking up the chapter 9 notes from Blackboard. Okay. So hypothesis testing is a decision-making process. It's a decision-making process for evaluating claims about a population. So we're going to call these conjectures. Statistical hypothesis is a conjecture about a population parameter, and the conjecture may be true or it may be not true. So there are two types of hypotheses that we're going to identify. So our goal in hypothesis testing is to use a statistical testing procedure, which requires that we lay out all of our information in a certain format. It's like a template. And then use this process to make a decision. So it's almost like you get everything organized, and then the process itself comes out with some statistical values, probabilistic values that help you to make a decision. So our first goal is to set up all the little pieces that are needed in the template to make the process work. So we begin with the identification of hypotheses that we will be comparing. The null hypothesis is the status quo. It's the established value. So the null hypothesis, we call it H naught, H with a little 0, and it's the hypothesis to be tested. The alternative hypothesis, denoted HA or H1, is the hypothesis that we want to consider, that we're interested in as an alternative to the null. So I set this up in the notes with 3 basic examples, okay? So in the null hypothesis, right? So in this case, we're always, in the situation in chapter 9, we will always be talking about making hypotheses about the population mean. So all 3 of the examples that I lay out here are about hypotheses, pairs of hypotheses about population mean. All right, so in the first case, we are interested in answering the question, does a new medication affect the pulse rates of those who take the medication? We know that the mean pulse rate for the population under study is 82. So the null hypothesis is that it does not have an effect, that the mean of the population is 82. And the alternative of hypothesis is going to be some alternative to equality. So one kind of inequality. So when we think of ways in which numbers are unequal, we have the not equal sign, less than sign, or the greater than, right? So things could be 3 ways we can describe an alternative to equals, would be not equal, less than, and greater. So when we look at the problem statement, we need to find a keyword, which I have here bolded, affect. We are interested in knowing whether or not the new medication affects the pulse rates of those who take the medication. So the null hypothesis was that a status quo, mu equals 82. And so the alternative hypothesis that we're interested in is we'd like to flag whether the pulse rate went either up or down. So we want to make sure that that alternative hypothesis has the not equal sign. So this not equal sign here is attached to the keyword in the statement of the problem, and that keyword is affect. So does it affect, does it change it, does it make it go bigger or smaller? So we're interested in an alternative hypothesis of not equal to. Then we look at the second example here. An alternative is being considered that will increase, an additive is being considered that will increase the life of the automobile battery. if the mean of an automobile battery is 36 months, then the hypotheses are that mu equals 36 as a null hypothesis, right? Because that's the status quo. And the alternative that we're interested in is has to be identified, finding the keyword first. In this case, I bolded it up, it's increase. And so an additive is being considered that will increase the life of the automobile battery. So the alternative to equals 36 is going to be greater than, because increase and greater than are, they go together. Okay, and so since we're only interested in increasing the life of the batteries, the alternative hypothesis is that the mean is greater than 36. Okay, so now we look at this third example. A contractor wants to lower heating bills using a special insulation. Okay, the average heating bill is $78 for the population of interest. And so the alternative hypothesis in this situation is it needs to be determined by the keyword lower, so it's less than. The alternative hypothesis is that mu is less than 78. This is also a one-tailed test, and since the only interest is in lowering the heating costs. So as we see, null and alternative hypotheses are always stated together. The null hypothesis contains the equal sign, and the alternative hypothesis has the not equal sign, not equal or greater than or less than. And we will go over why these are referred to in terms of tails, and we'll be getting to that shortly. Okay, so I want to just jump in and go over this basic logic of hypothesis testing, which is another way of saying this isn't how we're going to do it. It's more of a logical perspective, and in the next section, I'll set up like a structure, an algorithm, or strategies numbered 1 through 6, right? And to help us stay on track with hypothesis testing. But right now, we're just sort of thinking about it. Okay, so the way this works is we're going to take a random sample from a population. And if the sample data are consistent with the null hypothesis, then we do not reject the null hypothesis. If, on the other hand, the sample data are inconsistent with the null hypothesis in the direction of the alternative, then we will reject the null hypothesis and conclude that the alternative hypothesis is true. So I want to give this example about pretzels. Okay, so a company that produces snack foods uses a machine that packages 454 gram bags of pretzels. So we're going to assume that the net weights are normally distributed and that the population standard deviation of all such weights is 78. Okay, I'm going to take a random sample of size 25 of bags of pretzels, and they're displayed in the table below. Okay. So here are 25 weights, and the mean weight is 450 grams. And so he's very interested in hypothesis testing. Okay, and we want to answer this question. Do the data provide sufficient evidence to conclude that the packaging machine is not working properly? Okay. So what we want to do is we want to set up, given this question, this information here, we want to set up null and alternative hypotheses. So let mu be the mean net weight of all bags packaged. And then what we're interested in is identifying if the machine is not working properly. So the null hypothesis is that it is working. And the alternative hypothesis is that it's not working, so that the sign is not equal to in the alternative hypothesis. Mu equals 454 grams indicates that the machine is working. That is the null hypothesis. The alternative hypothesis is that mu does not equal 454 grams. The machine is not working properly. Okay, so I guess I'll put this a little bit in context. And when we think about this, right? So if you want to think about yourself as the manager of this packaging company, right? So you come in and you're in charge of getting, the packaging of these pretzels. And you have folks that work in your shop with you, and your job is to make sure that, or, do some kind of process to check that the null hypothesis, that the machine is working properly. That is, you walk in and you test to see if mu is in fact equal to 454 grams. If it is equal, you want to just keep going. You don't want to, take everything down and recalibrate it, because that costs both time and money. So you walk into the shop and you want to make sure, you want to have some evidence. So you're going to look at these 25, you grab these 25 bags of pretzels and you weigh them. And you want to, let's go ahead and look at the notes. So we have a null and alternative hypotheses and the logic behind carrying out the test. If the null hypothesis is true, we would expect that the sample mean is normally distributed with a mean of 454 grams. That's the null hypothesis, right? So if the null hypothesis is true, X bar is normally distributed with a mean of 454 grams. Now what we're going to do is we're just going to look at that X bar. We're going to look at the sample mean. And if the sample mean is too different than the population mean, mu, under the null hypothesis, in this case, 454 grams, then we can reject the null hypothesis. But the statistics comes in deciding how much is too much. All right, so if we think about it like this, we think, for example, that if we had gotten an X bar of, say, 300 grams, we would be pretty certain that the machine isn't well calibrated, okay? So if we have this pair of null and alternative hypotheses, and then we go and we take a sample of 25 and we get an X bar of 300, we're like, oh, reject the null hypothesis. It's totally not working. But then think about it. If it was 350, we want 454 grams as the mean, and now my X bar is coming in at 350. I still think it's broken. Maybe you don't, but I do, okay? And then we might get closer. 400 gram of the average is 400 grams. It seems a little light. I hate it when I get a bag of pretzels and there's not enough pretzels in there and I feel like I got ripped off, right? So you don't want to be there. You want to be like, how close can we get before we think that the machine is working correctly? Does it have to be 425, 430, 440, 450? That's the data that came out in our experiment here. In our data set, that is, if I scroll back up, we see that this sample is size 25 has a sample mean of 450. Well, it's not exactly 454 grams, but is it close enough so that it seems normal or reasonable that this would be the mean of 25 bags of pretzels? Okay, so that's what we have to decide. And what we're going to start doing is we're going to lean here on the distribution that we know about the parent population. We'll call this the parent, the population of all bags of pretzels. That's the parent population, right? And what we know here is we assume that the net weights are normally distributed and that the population standard deviation is 7.8 grams. So we are going to work with that information to help us make a decision to determine if we think that when X bar comes in at 450, is the machine broken or is it not? Okay. So I'm going to move over to the whiteboard and pick it up over there. All right, so what we know about a population of pretzels is that the parent population has a shape of normal. It's a normal shape distribution. Um, the mean is unknown, but under the null hypothesis, and maybe what we'll hold on to for right now, is that under the null hypothesis, the mean is 454 grams. That is the null mean. The standard deviation for the parent population is 78. And the sample size of the is 25. We took 25 bags of pretzels. All right, so we have the parent population, the distribution of X bar. So we're using results from chapter 7 here. Under the null hypothesis, the distribution of X bar is 454 grams. We really don't know that that's the case because that's why we're doing this hypothesis test, but we're going to set up with believing for a moment that the null hypothesis is true and looking to the data to see if we have enough variation from the null hypothesis so that we would think that the machine is uncalibrated. Give everybody a coffee break while you go and fix the machine, right? So you don't want to do that unless you have evidence that it's warranted because you lose, profit and all. So, so the distribution of X bar under the null hypothesis is 454 grams, and the standard deviation of X bar sigma over the square root of n, 78 over the square root of 25. Let's see what that is, 1.56. Now, we see that what we did observe is that we have, this is the mean, right, at 454 grams, and that's the null mean, and we did observe that 450, right, so that was our observation, and I'm not going to leave that there, well, I can leave that there. We need to come up with some criteria to determine how far away X bar has to be before we take that machine down and recalibrate it, right? And so we get to decide, maybe the boss gets to decide, right? The upper management might decide how much evidence we need that it warrants recalibrating the machine. But for this example, working from the notes, we are going to we obtain a precise criterion for deciding whether or not to reject the null hypothesis. And what we're going to use is we're going to recall the second part of the empirical rule that 95.44% of the time, a normally distributed random variable is within 2 standard deviations of the mean. So let me go ahead and draw that out. So let's figure out what 2 standard deviations is. We have 1 standard deviation is 1.46, and we want to go over 2 standard deviations in each direction. So I will take that out just so we don't have too much going on the graph. So that's 3.12. I'll put the note here. 2 sigma sub X bar is 3.12. So I want to add and subtract 3.12 from 454 grams and just put this on the table here. On the graph here. So if we come down this much, so we have 454 minus the 3.12, 450.88 on that side, and over here, this is really a 2 sigma, so it's more like that. And over here, this is 454 plus 3.2, so that would be 457.12, and just so you see where that comes from. So I'm just adding the 2 sigma to each side. So because of the empirical rule or the normal calculation, we know that that area there it occurs with 95.44% of the time. We would expect the X bar to be in this interval. Okay, so my criteria for rejecting the null hypothesis and concluding the alternative is going to be that if my X bar is outside of that 2 sigma interval, then I'm going to want to recalibrate. Let's go ahead and just clarify the null hypothesis here on the board. I know we had it on the notes, but I just want to put this here. Okay, so we do see that if our interval of interest here is 450.88 to 457.12, and at the X bar that we observed, right, we observed an X bar of 450, then we do see that that X bar is not within the interval, that 2 sigma interval that we had chosen as the precise criterion for rejection of the null hypothesis. So what that means is that we would reject the null hypothesis and conclude the alternative, and then you have to send the guys out on coffee break, recalibrate the machine, and get the day started late, okay? So I just want to also look at another way of seeing that our X bar is more than 2 standard deviations away from the mean. We do see that here because this is the 2 standard deviation interval. And then our X bar fell over there on the left. But what we could also do is we can calculate the z-score for 450, right? So we have z is equal to X bar minus mu. In this case, we'll take mu naught because under the null hypothesis, that's what the mean is. And that's what we're testing, divided by sigma over the square root of n, okay? So we substitute that in, right? You know, we're working on a z. So we're over here. And again, guys, this isn't necessarily exactly how you're going to be doing the hypothesis test. So just try to get the overview of what's going on. We already actually figured it out, but I do want to use the z-score, bring it over and show you whether or not z is greater than or less than in that between -2 and 2, more than 2 standard deviations away from the mean. So we have 450 minus 454 divided by sigma over the square root of n. So that's 78 over the square root of 25. We already calculated it once. It's 1.56. So calculating this, we get a z-score of -2.56. So we come on over here, and what we had agreed was that if my X bar was more than 2 standard deviations away from the mean, then we would reject the null hypothesis. So let's go ahead and draw that up on our picture. We had this whole area here. We decided we would reject if it was between -2 and 2. We were going to reject the null hypothesis. And if it was outside that -2 to 2 interval, I got it wrong, right? So we decided that if X bar was between -2 and 2, we would not reject. Do not reject the null hypothesis, right? So we calculated this, and what we see is that z is equal to -2.56, right? And so it's outside the region of not rejection. So here we're going to have to reject the null hypothesis because that's where our z-score fell. It's outside the 2 standard deviation interval. Okay, so we're going to pick this up in the next video. We have a general overview, and now we're going to continue to work through the different components in section 9.1. We're going to work through the different components of hypothesis testing. And then, but the video is getting long, so I'll see you in the next video.